Hey, welcome back, everybody. Today we're going to take a look at what is this? Section 5.2. Woo, binomial probability distributions. One of my favorite sections in here because I don't know why. I just get a kick out of these things. All right, so in our session today, we're going to take a look at some key concepts. That is to take a look at what does it mean to be a binomial probability problem and, more importantly, a binomial probability distribution. And we'll take a look at methods for finding probabilities of those binomials because you got to have the methods to make the distribution. Okay. We'll take a look at some very simple, super easy methods for finding the mean of the standard deviation of a binomial distribution. And then we're going to take a look at the idea of in stressing the importance of those significantly low or significantly high, what that means. All right, so first things first. What the heck is a binomial probability distribution? A binomial probability distribution will be the distribution that we get from a process, from an experiment, from a procedure that meets these following four requirements. First off, number one, the procedure has a fixed number of trials. What does that mean? So imagine our experiment was to flip a coin 10 times. Fixed number of trials being the 10 times, the experiment being the flipping the coin, right? So a trial is one run or one observation of our experiment, right? Number two, the trials must be independent. So if I'm flipping a coin, the first time I flip it, whether it lands heads or tails, should not affect the second time I flip the coin. So independent means if the coin lands head on the first time, that doesn't affect that it'll be a head on the second time or tails on the second time because it doesn't. Right? And if you're thinking, oh, does it have to be coins? No, it could be anything. I could roll a die. And no matter what I roll on the first roll, that shouldn't affect the second roll. Independent. Right? Here's where things get a little tricky. Each trial must have outcomes that can be classified into exactly two categories. We commonly refer to these as success and failure. So if I had the experiment roll die, I don't know what, 5 times, and I wanted that to be binomial, my sample space, I'd have to write it somehow so that I only had 2 outcomes every time I rolled the die. Right? And now I know at least one person is thinking, wait, there's 6 sides, 6 faces on a die, so there's 6 outcomes every time. No, I've got to write my experiment in such a way as there's only 2. So I would say my experiment is to roll a die and count 2s. So now every time I roll the die, it's either success because I rolled a 2, or it's failure because it rolled anything other than a 2. Right? Also, the probability of success, and of course then by definition also failure, has to stay the same for all the trials. Meaning if the chance that I roll a 2 on the first try, the first trial, is 1/6, it better be 1/6 for every single time I roll that die. Okay? I'm going to try that again. Notation for binomial probability distributions. S and F stand for success and failure. Those are going to show us our 2 possible categories of outcomes. P of S, the probability of success, we're going to call that lowercase p or little p. P of F, the probability of failure, we're going to call that little q. Okay? So when you see small p's and small q's, probability of success, probability of failure. The letter N is going to stand for the number of trials of the experiment. So if I'm rolling the die 5 times, N would be 5. Okay. Our random variable X, it's going to count the number of successes that we see. So X is going to be a specific number of successes in those N trials. Right? So that means that X can only be a whole number because you can't have half of a success. A trial was either successful or it wasn't. Right? And then the P of X is just going to be the probability of getting that random variable X number of successes. Right? Now, one thing that people sometimes get stuck on is they think that this means good, and that means that failure is bad. No, success and failure here are just words we use to talk about. There's two outcomes. Call this thing success, call that thing failure. All right. All right. Let's take a look at an example. Here are some scenarios. Our job is to determine whether these scenarios are binomial. If they are, find the n, the p, the q, and talk about what x could be. All right, so we'll read the first one together. A survey found that 36% of frequent gamers play video games on their phone. 10 frequent gamers are randomly selected. The random variable represents the number of frequent gamers who play video games on their smartphones. So it looks like I asked 10 frequent gamers, hey, do you play video games on your smartphone? And the answer to that was either yes or no. Two possible outcomes. We'll see here, since they want the random variable to represent the number who play video games on their smartphones, that success is they said yes. So this looks very binomial. It looks like we're running this experiment 10 times because I talked to 10 people. It looks like the probability that they will say yes, they do play smartphone games is 0.36 from that data that was collected in the survey. It looks like the probability of failure, that is that they will say no, I don't play, would then be 0.64. Remember, P and Q, success and failure, cover the only possible outcome, so they must add up to 1. And it also looks like then that X, our random variable, could be 0, or it could be 1, or 2, or 3, or all the way up to a possible 10. Each of those values tells me how many times I got a yes success answer. So a random variable value of 0 means that I talked to 10 people and they all said no. A random variable of 1 means that I talked to 10 people and 1 of the 10 said yes. Now the thing you have to be careful about here is binomial doesn't tell you when success happens. It just tells you that success does happen. And what I mean by that is a random variable value of 1 means 1 person said yes. 9 people said no. But I don't know which person said yes. I don't know if it was the first person or the 8th person or the 3rd person I talked to. Binomial doesn't do that. If you want to put success in a specific location, that is in the first person you talk to or in the 4th person you talk to, that's a different thing. That's a geometric distribution. These are binomials. So keep that in mind. Success can happen anywhere. Right? And then, of course, it ends up here at 10. And what would that mean? Well, that would mean that all the people I talked to, all 10 said yes. Right? All right. Let's take a look at the second example. So that was definitely binomial. Let's look at one that isn't and see why. Okay? You draw 5 cards. Well, that sounds good. I'm doing an experiment 5 times. Right? One at a time from a standard deck. You do not replace the cards once it's been drawn. The random variable represents the number of cards that are hearts. Okay? Well, that's not binomial. The reason it's not binomial is right here, and I'm going to underline it in blue. One of the requirements for binomial is that the trials are all independent. If I pull a card out of the deck, the first time I pick, I got 1 out of 52. There's 52 cards in the deck. I'm looking for a heart, so I have all 13 hearts in the deck to pick from. So my probability of a heart on that first pick would be 13 out of 52. But if I don't replace that card, then when I pick the second time, I no longer have 52 cards in the deck. And depending on whether that first card was a heart or was something else, it might be 13 out of 51 if it wasn't a heart, or only 12 out of 51 if it was a heart. So since the second card, the second pick, the second trial, since those depend on the outcome of the first, this is not independent. Therefore, it is not binomial. This is a very complicated probability problem that is not a binomial one that we won't do. All right, move on to the third one. A state lottery official randomly chooses 6 balls. Okay, 6 trials of the experiment. Pick 6 balls. Without replacement, oh, right there, boom, done. Without replacement is the same problem as last time. The reason this is not binomial is because I didn't put them back. That means when I pick the second ball, all of the probabilities have to readjust depending upon what the first ball was. So not binomial. Okay. Let's take a look at the last one. A survey found that 43% of women aged 18 to 33 are mothers. 8 women are randomly selected. Okay, that looks good. I'm picking 8 people and talking to them. And my random variable represents the numbers who are mothers. Well, doing the same thing 8 times. I'm grabbing 8 women from and saying, hey, are you a mom? 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 The answer can be either yes or no. Okay. Success and failure. See, this is one of those ones where using the word success and failure is kind of weird. Is it success to be a mom? Or is it failure to be a mom? Now, if you're going to go, well, being motherhood is not a failure. Well, is not having a child make you a failure? So this is where people get kind of upset or can be upset by those words success and failure. Okay. So keep in mind, success in this sense does not mean good. Failure does not mean bad. Success just simply means that you defined what you're counting, and it's success if you can count that. So this looks binomial to me. With an n of 8, a probability of success, meaning they will say they are a mother, of 0.43, which means that failure would be 0.57. And it looks like x could be 0 or 1 or 2 or ... all the way out to 8. Again, what does a 0 mean? It means I talked to 8 women, and all 8 of them said I'm not a mom. A 1 means I talked to 8 women, and 1 out of 8 says she's a mom. 2 out of 8, and so on and so forth, all the way up to a possible 8 out of 8. Okay? So that would be binomial, and there's everything that we need to make that problem work. All right. Let's look at an example where we're going to take a binomial scenario. So we're being told that it is binomial, and we're going to ask a probability. All right. So rotator cuff surgery has a 90% chance of success. All right. So they're going to cut into your shoulder and fix a problem with the rotator cuff, which is the sac in the shoulder that kind of helps hold things together, whatnot. All right. There's a 90% chance of success, meaning that the surgery will make your shoulder better. It also means there's a 10% chance of failure. The surgery is performed on 3 patients, so we have 3 trials of the experiment. We want to find the probability. We want to calculate a probability of successful on 2 patients. All right, so N is 3 patients. P is 0.9. Q is 0.1. And X could be 0, 1, 2, or 3. Those are all of the possible outcomes. We just want to find this probability. The success happens twice. Right? All right, so how do I do that? Well, there's a formula for it. The binomial probability formula tells you to do this. That the probability that you will see X successes, so remember that means it could be 0 or 1 or 2 or 3 for this experiment. You're going to find n factorial. Okay, so does this notation ring a bell with you, this exclamation point? That's factorial notation. So like 5 factorial means 5 times 4 times 3 times 2 times 1. You just start with that number, times 1 less, times 1 less, times 1, until you get to 1. Right? Same thing down here in the denominator. You can do n minus factorial and x factorial, and then probability and success P and Q raised to exponents. So for our example, if we want to find the probability that x is exactly 2, we're going to do 3 factorial divided by 3 minus 2 factorial times 2 factorial times 0.9 to the second times 0.1 raised to the 3 minus 2. All right, so here, 3 factorial. That means 3 times 2 times 1, which is 6. 3 minus 2 is 1. 1 factorial is 1. 2 factorial means 2 times 1, so that's just 2. Right? So this becomes 6 over 2 times 0.9 squared times 0.1 to the first power. 3 minus 2 up there is 1. Right? I'm going to need a calculator for that. Not the 6 divided by 2 part. That's going to be 3. I can do that. Times 0.9 squared times 0.1. And I get 0.243. Or, if you want to think about this in terms of what it means, is that even though this surgery has a 90% chance of success on one surgery, there's only about a 24% chance that if I perform this surgery 3 times, that it'll be a failure once and successful twice. Now that number seems awfully low, especially considering we're looking at a 90% chance of success. Trust the math. Right? There's a lot going on here. And I'm going to erase this and show you why I say there's a lot going on here. Right? Let's see, delete. If we think of this in terms of a tree diagram, surgery 1 could be success or could be failure. Surgery 2, success, failure, or success and failure. So the blue represents the possible outcome if I have one surgery. The green branches now say, well, there's now 4 possible outcomes if we have 2 surgeries. We could have one path up here that is success, success, or success, failure, or failure, success, or failure, failure. 4 different possible paths that could occur. If we add in a third surgery, success, failure, success, failure, success, failure, success, failure. Now we've got 1, 2, 3, 4, 5, 6, 7, 8 different possible outcomes, ranging from the optimal success all 3 times to the suboptimal failure all 3 times, and then everything in between. Now, our job was just to find the probability of 2 successes. Well, that's this branch, or this branch, or this branch. There's 3 possible outcomes that have 2 successes and 1 failure. Do you remember when we did the calculations how we had that 3 sitting out in front after we did that fraction? That's where the 3 came from. And then in all 3 of those paths, there are 2 S's and 1 F. So we need an S, and an F. Well, S is 0.9. So that's the 3. There's the 0.9 squared, and F was 0.1 to the first power. Right? Now, drawing out tree diagrams and figuring out this way is fine if n is small. But what if we change this experiment and say, what if we had 30 surgeries? I don't want to do that. I don't want to draw out the diagram for this. I also don't want to do that formula up there. I don't want to do that math for 30. I don't want to figure out what 30 factorial is. So luckily for us, the good people at TI thought, hey, you might want to do this. So they built it in. So here's where it's hidden. See above the variables key where it says distribution there? If I go there to the distribution and I scroll down, I'll find something called binomial PDF, my binomial probability density function. That's the fancy way of saying this guy. I'm going to grab that, and it's going to ask me, how many trials? Well, we did 3 trials. What's P? What's the probability of success? Well, that was 0.9. And what did we find? What did we want to find the probability of? Well, we wanted to find the probability that our random variable was 2, or that we had 2 successes. And I'll paste this back in, and it pastes it back into the home screen, and then I'll press enter again, and it tells me 0.243. It is just doing this formula right here for us. That's all it's doing. So then the probability that x equals 2 is 0.243. Or if you want it in words, the probability of exactly 2 successful rotator cuff surgeries is 0.243. Although I might argue that since the problem was set up in percents, I would give them back their answer as a percent and say it's 24.3%. Right? These are binomials. They can be calculated by hand, and that works fine. The formula is kind of clunky and awkward if you have to do the formula for big sets. For large number of trials of the experiment, the formula gets ugly. Right? Use the calculator. You may have noticed when we were doing the calculator, it never asked about Q. It just asked for P. Well, honestly, if you know P, you know Q. Because the definition says that Q is just 1 minus P. All right, let's take a look at a different couple examples here. All right, 36% of U.S. adults favored the use of unmanned drones by police agencies. You randomly select 9 U.S. adults, find the probability that the number in favor of the use. Wow, that really does not read well. That's supposed to read, find the probability that the number that favored the use of drones. That should be a that. The use of drones is, and then all of these possibilities right there. Okay, I paused the video and fixed that on your end. So hopefully when you download this, you'll see a that there. All right, so first off, let's get this thing set up. I'm reading binomial, where I am talking to 9 people. The probability that they will say yes is 0.36 from before data, from, what was that? Statistical probability calculations, which means the Q is 0.64. Not that it matters because I don't need it for the calculator. And then X could be 0 or 1 or 2 or 3 all the way up to 9. Right? The first one wants us to find the probability that X is exactly 4. Now I could do this by hand with the formula, and that's great. I'm not going to. I'm going to use my calculator. I'm going to grab my calculator. I'm going to, what am I going to do? Hold on a second. All right, that's better. I kind of readjusted the window here so the calculator isn't on top of what we're saying. Right? I'm going to calculate that binomial PDF. So again, it's that distribution menu that's above the variables key. So second, distribution. I'm looking for a binomial PDF. There it is. Trials is 9. Probability of success is 0.36. I want to see 4 successes. Paste that, press enter, and I get a probability of 0.227, we'll call it. Or since our data was given to us as percents, we'll say the probability that 4 people of the 9 people will say yes is 22.7%. Which 4? Don't know. Could be the first 4, could be the last 4, could be the middle 4, could be 4, 4, 4, 4, 4. Don't know. 4 of them are going to say yes. Right? Part 2, or part B, if you want to think about that, they want us to find the probability that less than 6. Okay, Well, what does less than 6 mean? What's the probability that x is less than 6? Well, less than 6 would be what? 5 or 4 or 3 or 2 or 1. So that means we need to find the probability of 5 plus the probability of 4 plus the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0. I'm not doing that. That is way too much work. I mean, I could. Like if I had nothing else to do all day, I could sit and just punch numbers on my calculator. I'm not going to do that. And luckily, the good people at TI feel exactly like I do. So let me get rid of this. And let's take a look at how we're actually going to calculate this. So first off, can we all agree that less than 6 means the probability that x is less than or equal to 5? And the reason I need to do that is I need to find the highest number that I'm going to let x be. In this case, the biggest number that x could be is 5. So I'm going to go back to the same place I went before. I'm going to go to my distribution menu. And I'm going to scroll down. But this time I'm not looking for binomial PDF, which finds a single value like we did here. I'm looking for binomial CDF. And what that's going to do is it's going to calculate the probability that x is 0 plus the probability that x is 1 plus the probability that x is 2 and 3 and 4. And it'll keep finding all those left tail probabilities until we tell it to stop. In this case, we're going to tell it to stop. We are going to tell it to stop at 5. Okay, so I'm going to punch that up. Now, one thing to be careful of. This screen looks exactly the same as the screen looked for the first part. The only difference is way up at the top, right up there, there's a little C instead of a P. There's still 9 trials. It's still a 0.36 probability of success. But when I put a 5 there, I'm not telling it just to find 5. I'm telling it to find 5 and everything else below 5. Paste it back in. See up there, binomial PDF, down here, CDF, enter, and I get that this is, I'll just put it straight as a percent. What is that, 93.9%? Okay. That means that if I knock on 9 doors, I've got about a 93.9% chance that 5 or fewer people will say yes, that police should use unmanned drones. Right? Moving on to the last one. At least 2. Well, that's going to be tricky. Okay, this one was a single value. This is a left tail because it's asking for 5 and below, moving to the left. If we think of a number line, right? We're starting at 0. We're going out to 9. We want from 5 and we want left of that. So that second one, that's a left tail one they want us to calculate. If we look at what they want us to find in this third part, at least 2, that's a right tail. At least the probability that x is greater than or equal to 2 would be 2 plus 3 plus 4 plus all the way out to 9. Now, unfortunately, the good people at TI did not expect you to want to do this, so they didn't build it in. Right? But we can cheat. And I say cheat, but we're not really cheating. We're using rules of probability to make this calculation simpler. And what we're going to use is we're going to use the complement rule, that the probability of greater than or equal to 2 is 1 minus the probability that x is less than or equal to 1. And this is that problem again, but just with a 1 instead of a 5. And I can find that. I can go to my distributions. I can go to my binomial CDF. I can change that 5 to a 1. I can get that probability of 10.9%. And then I can say, well, that just means that it's 1 minus that, or 1 minus that answer. So 89.1%. Okay. These are the three different versions of a binomial problem that can be asked. The first one is an exact value. The second one is a left tail problem. The third one is a right tail problem. And that's it. I'm going to guess technically someone could be mean and give you an in-the-middle problem, but we don't do those very often. Okay. All right, moving right along. I want to do this one. I know the video is kind of long. I'm going to finish this one really quickly, and we'll end the video there and start up for the next one. Okay. 56% of people say they're going to get a flu shot. We talked to 10 results. We want to find the number who get a flu shot. We want to find the probability of those numbers. Binomial. N is 10. P is 0.56. X could be 0 or 1 or 2 or all the way up to 10. The first one asks exactly 4. That's a binomial PDF problem. So PDF single value problem. Go to my distribution, find that binomial PDF, trials 10. Whoops. Trials 10. P 0.56, X value 4, paste, paste, paste. We're looking at 15.0%, and we're done. Less than 7. Less than 7 means 6 and below. So the probability that X is less than or equal to 6. That's a CDF problem because it's a left tail, right? So grab my calculator, go to my distribution menu, find the CDF command, 10 trials, 0.56 probability for success. My highest value is going to be 6. Boom, boom, boom. 71.2% chance. Okay? So this is the most common mistake in this problem, is reading this wrong. Less than 7 means 6 and below. So be careful with that. Okay? All right. Last one, at least 8. So that means we want the probability that X is greater than or equal to 8. Right tail problem, can't do it directly on the calculator. So I'm going to rewrite it as 1 minus the probability that X is less than or equal to 7. Turning a right tail problem into a left tail problem because the calculator can do that. So back to my distribution menu, back to binomial CDF, change that value to a 7, 10.567, 88, 1 minus that, and I get 11.1%. So this is binomial probability. These are very straightforward problems. We'll come back for part 2 of this video and look at more complicated ones. See you then.